Welcome back, geology fans. I have a confession that I have not been completely honest with you. I have been using this grid and calling it a Stereonet the last few episodes. With true stereographic projections, the intersections of lines and planes hitting the bottom of our bowls are projected back to the top of the sphere and imaged through the equator. This results in what is called an equal angle projection stereonet, so that spatial measurements, such as angles of intersecting planes and lines, as they are read on the plot, will be the same as the angle of those features in the real world, which is useful in a field like mineralogy or crystallography. This true stereonet is also known as a wolf net. But an equal angle wolf net projection does not produce equal area on the plot, so that the spread of a concentration of points can vary in size up to a factor of 2 depending on where it is on the net. Because of this, a true stereonet showing equal angles is not so useful for clustered data analysis and structural geology. When I collect a lot of structural data and want to know preferred orientation of some features, like average dip of beds or most common orientations of faults, folds, or joints to get paleostress information, then it's nice to use an equal area projection, also known as a Lambert projection, which makes a plot called a Schmidt Net, which is projected below our sphere instead of the projection plane being through the equator of the sphere like the wolf net. The plotted point is also on a circular arc that would go through the center of the sphere, and so is not truly a stereographic projection. For this reason, only wolf nets are technically stereonets, and Schmidt nets should be called just equal area plots. But we geologists get a bit lazy and call both of these stereonets. So forgive me for having called this Schmidt net a stereonet all this while, and for continuing to do so. And so today I want to point out another use and great advantage of a Schmidt equal area stereonet. A cluster of points will not vary in size depending on placement, and true patterns can emerge from large data sets. We will be plotting poles of planes for the most part in such statistical analyses, so we should imagine the planar features we may be measuring as having these poles perpendicular to its surface, and think about how these pole clusters would plot on our stereonet. Uniformly tilted layers of rock will plot as a cluster of poles on one area of the net, and on a Schmidt net we know that the clustering density is a true statistical measure and not a function of placement on the grid. Let's make this a little more interesting by folding our layers with a horizontal axis, and the poles to the plane will plot as a linear cluster of points across the net through the center of the grid. But we can see that some areas are denser in points than others, and to get an even better look at this clustering, we can use something called the Schmidt method to contour out the discrete points into areas of density, which involves counting up the number of points per gridded area of a plot, then making a contour map, as we did for topographic maps way back in episode 8 of this series. And for horizontal folds, we get hills of data clustering around here and here, with an intersecting elongation. There are other ways of contouring data, but honestly, contouring data is a job better suited for computer programs these days, so let's not get bogged down. We contour the data to better see if there is a pattern in the data, such as the point cluster of our uniformly tilted beds. And if you get more than one cluster, that's always interesting in your data set. It could definitely be produced by angular unconformities or by fault tilting. That could be at play. Perhaps you already knew that, or perhaps you need to head back out into the field with this new insight from your Stereonet. Even more interestingly, you might get patterns of small circles and great circles, with data concentration blobs around parts of those arcs. To better understand all of this, we need to go a little bit deeper into folds. We've seen folding as a ductile response to compression in rocks and saw many types, but we can say there are two main types of folds: cylindrical folds. Tangential planes to the flanks of the fold would intersect in a line parallel to the fold axis for the cylindrical fold. and non-cylindrical folds, of which there can be many types. One non-cylindrical subtype, the conical fold, produces data that scatters around our net in small circles. But cylindrical folds make great circles. Using poles instead of planes, a flat surface would make a small area of data, but as we fold it, the circular area spreads out in a short line, and the steeper the limbs of the fold, the farther across the plot our line of data becomes. And with horizontal folding, the line goes through the center of the plot. And we call this line the girdle of the bedding poles for that fold system. But as we go from a concentric normal fold to narrow hinge to a sharp angled chevron fold, the data concentrates, then separates those blobs on each end of the girdle, which is another way to get two clusters of data. The two blobs created by chevron folds do still lay on the great circle girdle of the fold axis, though. When recently working on mapping the fold that can be seen in this scene from Mullis Lake, Colorado, can you see it? We were advising our students to take copious measurements around the axis of the fold and not as many around the relatively straight limbs of the fold. But you should note you are doing this as it increases the points through the girdle of the fold data and can throw off true clustering patterns. If you want a perfect data set for contouring, ideally you should evenly space out your measurements as much as possible. We rarely do, but this clustering is easily seen in our maps, and we must keep this in mind when clustering our data. Did our clustering of data in the field cause artificial clustering of data in our Stereonet? All this must be noted when contouring data. Asymmetric, cylindrical folds will have stronger concentration on one end of its girdle than the other. One data blob will be larger with asymmetry. What if our horizontal normal folds go to plunging normal or plunging inclined folds? As we plunge off horizontal, our clustered data poles pull off from the center of the plot and start showing shallower, great circle girdles. Again, we get two blobs on the ends of the girdle, and the amount of data connection between can indicate tightness of the angle of the fold axis. And if one blob is larger than the other, you know that it is not only plunging but inclined asymmetrically as well. So the same principles hold for the horizontal folds, but now the girdle of the fold is on a great circle that is off-center. And if the plunging folds are overturned, we see the data wrapping its girdle all the way around, possibly splitting one of its data blobs across the other side of the net. Other possibilities are the reclined fold, which will group data towards the center of its great circle, perhaps forming a single data blob, or the recumbent fold with two blobs so close together it looks like a cross-eyed Teenage Mutant Ninja Turtle mask, that still lays on a great circle, telling us something about our folds. Once you can see such a girdle of data for your fold, you can start to work out the orientation of the axial plane of the fold, which you will recall is a bisecting plane of symmetry through our folds. You will need to have measured the fold axis direction to do this, but just a direction on the compass rose will do it. You then plot your poles, and if you find a girdle of data, you can find the great circle that goes through that girdle. And now plot the pole to that, which takes us 90 degrees off of our bedding poles to line up with our fold axis. This is called the pi axis. Put another point on the outer edge of our circle to mark the fold orientation that you measured, and mark it O for the orientation of the fold axis. And then find the great circle that passes through pi and O. This planar line represents the orientation of the axial plane of the fold. Some other statistical problems you might want to work out using an equal area Schmidt net might be a rock fabric or foliation, but there are really no new concepts there. Just plot the data and contour to look for patterns in the data set again. There are even more uses of stereonets, or Schmidt nets more properly, including stress analysis from faulting and folding, but that goes to a depth I'm not intending for this series, and there are a lot of good videos out there discussing stress elements, Moore's circle analysis, and stress analysis using Stereonet plots. No need to oversaturate YouTube with the same content, so I'm moving onward and upward to scratch the surface of our great topic as we dig into soil when we come back next time here on Earth Explorations.